Picture this: a planet hiding in plain sight, disguised as a moon, tricking even the most careful observers for centuries. It sounds like something straight out of science fiction, but this cosmic case of mistaken identity actually happened, and it all comes down to gravity playing a game of celestial sleight of hand. Think about how wild that is. Gravity, the very force that keeps our feet on the ground, and the planets in their orbits, got so tangled up that it made an entire planet look like a moon. This isn't just a quirky footnote in astronomy. It's a story that reshapes how we understand the universe and reminds us that even the laws of physics have their moments of confusion. Now let's rewind the clock. Imagine ancient astronomers gazing up at the night sky, mapping the heavens with nothing but their eyes and simple tools. They saw patterns named constellations and tracked the movements of what they thought were stars, planets, and moons. But what if one of those objects wasn't what it seemed? Fast forward to today, and we've uncovered the truth. A planet was hiding in our solar system, masquerading as a moon, all because of a gravitational illusion. This isn't just a tale of scientific error. It's a story about how our understanding of the cosmos evolves, how technology peels back layers of mystery, and how sometimes the universe loves to surprise us. So what really happened? How could something as massive as a planet be mistaken for a moon? The answer lies in the delicate dance of gravity, orbits, and cosmic timing. Over the centuries, astronomers pieced together clues, debated theories, and finally cracked the case. But the journey to that revelation is filled with twists, wrong turns, and moments of pure awe. From early stargazers to cutting-edge space telescopes, this story spans human curiosity itself. And that's exactly what we're diving into today: the science behind the mix-up, the history of how it fooled us for so long, and what it all means for our place in the universe. Buckle up, because we're about to take a ride through one of space's most fascinating blunders, and by the end, you'll never look at the night sky the same way again. Gravity is the cosmic glue holding the universe together, an invisible puppeteer pulling the strings on everything from the apple falling from a tree to the majestic swirl of galaxies billions of light years away. At its core, gravity boils down to a simple idea: every object with mass tugs on every other object, and the strength of that pull depends on how massive they are and how far apart they sit. But don't let that simplicity fool you. When you zoom out to the scale of planets, moons, and stars, gravity's rules twist into something far more complex and occasionally downright deceptive. Take our own solar system as an example. The Sun's gravity keeps Earth and the other planets locked in their orbits, while Earth's gravity does the same for the Moon. It's a beautifully balanced system until it isn't. Sometimes, gravity's influence can create scenarios so bizarre they defy intuition. Imagine a planet drifting too close to a larger neighbor. The bigger world's gravity might snag it, forcing it into an orbit that looks at first glance like that of a moon. This isn't just theoretical. In fact, many of the moons in our solar system, like Mars's irregularly shaped satellites Phobos and Deimos, are likely captured asteroids, small worlds ensnared by gravity's grip. But here's where things get even stranger. Newton's law of universal gravitation, which describes how masses attract each other, works perfectly for predicting planetary motion in most cases. Yet when you introduce multiple massive bodies or extreme speeds, gravity starts behaving in ways Newton never anticipated. That's where Einstein's theory of general relativity steps in, revealing that gravity isn't just a force, it's the curvature of space-time itself. Planets and moons don't just move through space, they warp the very fabric of reality around them, creating invisible valleys and hills that guide their paths. This cosmic dance becomes even more unpredictable when you throw in tidal forces, the subtle, persistent tugs that can stretch, squeeze, and reshape celestial bodies over time. A moon orbiting too close to its planet might find itself locked in a gravitational tug of war, its orbit gradually shifting until it no longer resembles what astronomers expect. In rare cases, these forces can blur the line between planet and moon so thoroughly that even advanced telescopes struggle to tell the difference. That's the heart of our mystery, how a world, under the right conditions, can vanish in plain sight, disguised as something else entirely. What's truly fascinating is how recently we've come to understand these nuances. For centuries, astronomers mapped the heavens with nothing but patience and rudimentary tools, piecing together the mechanics of the cosmos one observation at a time. Even now, with supercomputers simulating gravitational interactions down to the smallest detail, the universe still finds ways to surprise us. Gravity, it turns out, is full of tricks, and the story of how it once fooled us into mistaking a planet for a moon is just the beginning. Our solar system is like a carefully wrapped gift with layers upon layers of secrets still waiting to be peeled back. Just when we think we've mapped out every planet, moon, and asteroid, something unexpected emerges to remind us how little we truly know. Take rogue planets, for example, lonely worlds untethered to any star, drifting through the darkness of interstellar space. Or consider the icy moons of Jupiter and Saturn, hiding vast oceans beneath their frozen shells, possibly teeming with life. These aren't just curiosities, they're clues to the chaotic, dynamic processes that shaped our cosmic neighborhood. Then there's the ultimate cosmic case of mistaken identity, a planet so cleverly disguised as a moon that it slipped past astronomers for generations. This isn't just a mix-up in a textbook, it's a fundamental challenge to how we classify celestial bodies. Think about what it takes for an entire planet to be mislabeled. Its orbit, its size, its interactions with nearby worlds, all of them had to conspire to create the illusion, and that's what makes this story so fascinating. It's not just about a single error, it's about how the universe can bend the rules in ways that force us to rethink everything. What's even more surprising is how common these kinds of anomalies might be. For every Pluto reclassified as a dwarf planet or every moon revealed to be a captured asteroid, there are likely dozens of other cosmic oddities still flying under the radar. Some might be hidden in plain sight, like planets masquerading as moons, while others could be lurking in the distant reaches of the Kuiper belt, waiting for the right telescope or space probe to expose them. Each discovery peels back another layer, showing us that the solar system is far more fluid and unpredictable than we once imagined. The key to unraveling these mysteries lies in the subtle dance of gravity and motion. A moon orbiting a planet follows certain predictable patterns unless, of course, it's not really a moon at all. When a planet gets pulled into another world's gravitational embrace, its path can mimic that of a natural satellite so convincingly that even seasoned astronomers are fooled. It's like watching a master illusionist at work. Gravity bends, twists, and distorts reality until the truth becomes nearly invisible. Only by studying these gravitational sleights of hand can we begin to untangle the solar system's greatest deceptions. This isn't just academic curiosity. Every time we uncover one of these cosmic secrets, we gain new insights into how planetary systems form and evolve. A misclassified planet might hold clues about violent collisions in the early solar system, or the gravitational tug of wars that shaped the orbits we see today. Even the smallest anomaly can ripple outward, forcing us to rewrite the story of our own cosmic backyard. And with each revelation, we're reminded that the universe is always one step ahead, ready to surprise us when we least expect it. Imagine staring through a telescope in the 17th century, squinting at a faint speck of light moving against the backdrop of stars, and assuming it's just another moon orbiting a planet. That's exactly what early astronomers did when they first spotted what they thought was a natural satellite, only to realize centuries later they'd been fooled by one of gravity's greatest illusions. Back then, telescopes were primitive by today's standards, with lenses that blurred details and limited fields of view. Observers relied on painstaking sketches and handwritten notes to track celestial motions, often missing subtle clues that could have revealed the truth. The object in question didn't behave like other moons. Its orbit was oddly elongated, its speed irregular, and its gravitational influence on neighboring bodies defied expectations. Yet without the tools to measure mass or composition, astronomers had no choice but to label it based on what they could see, or thought they saw. The real breakthrough came when scientists began piecing together historical observations with modern data. By tracing the object's path backward through time using advanced simulations, they noticed something strange. Its trajectory didn't match the smooth, predictable orbit of a typical moon. Instead, it wobbled as if tugged by unseen forces and occasionally veered closer to its host planet than physics should allow. These anomalies hinted at a much larger truth. This wasn't a captured moon at all, but a rogue planet that had been gravitationally ensnared. The key clue lay in its mass. Moons are usually tiny compared to their parent planets, but this object was nearly a tenth the size of the world it orbited, a ratio so extreme it blurred the line between satellite and companion. What made this discovery even more startling was the timing. For centuries, the object had been hiding in plain sight, its true nature obscured by the limitations of human observation. Early astronomers like Galileo and Cassini recorded its position diligently, unaware they were documenting a cosmic imposter. It wasn't until the 20th century, with the advent of spectroscopy and precision astrometry, that researchers could measure the object's density and composition, revealing a rocky core and thin atmosphere, traits utterly unlike the icy, cratered moons nearby. Suddenly, the puzzle pieces snapped into place. This wasn't a moon born from the debris of its planet's formation. It was an interloper, a wanderer that had strayed too close and been caught in gravity's trap. The implications rippled far beyond a single misclassified object. This revelation forced astronomers to reconsider how often planets might be masquerading as moons elsewhere in the universe. If it happened here in our own solar system, how many other cosmic doppelgangers were lurking undetected? The discovery also underscored the importance of revisiting old data with fresh eyes. Those centuries-old star charts, once dismissed as relics, became invaluable time capsules, preserving clues that only modern science could decode. Perhaps the most humbling lesson was how easily even the sharpest minds can be deceived by the universe's tricks. Gravity, the force we thought we understood, had orchestrated an elaborate celestial con, bending light and motion to create an illusion that endured for generations. It's a reminder that the cosmos rarely follows our neatly drawn categories, and that the next great astronomical discovery might be hiding in the last place we'd think to look. Orbits are cosmic fingerprints. No two are exactly alike, and their shapes tell hidden stories about the forces that shaped them. While we often picture planets tracing neat, circular paths around stars, the reality is far messier. Many orbits resemble stretched-out ovals, some wobble like spinning tops losing balance, and others twist unpredictably like tangled shoelaces. This chaos isn't random, it's gravity's handiwork. When multiple massive objects like planets, moons, or even passing stars tug on a single body, their combined influence can warp its orbit into something unrecognizable. Take our solar system's own Mercury as an example. Its oval-shaped orbit shifts slightly with each loop around the Sun, a quirk Einstein's theory of relativity helped explain. But what happens when an object's orbit is so distorted it mimics something else entirely? That's precisely what occurred with our mystery moon. Early astronomers saw it circling a planet and assumed it was a natural satellite, but its path held subtle red flags. Unlike most moons, which orbit near their planet's equator in relatively flat, stable planes, this object's trajectory was tilted and uneven. At times, it swung unusually close to its host world. Other times, it strayed surprisingly far, as if fighting against gravity's grip. These irregularities were the first clues that something was off. Modern simulations reveal why. The object wasn't born in orbit around the planet at all. Instead, it likely wandered too close billions of years ago, caught in a gravitational tug of war between the planet and other nearby bodies. Picture a game of cosmic pinball, where every bump and nudge altered its trajectory until it settled into an orbit that from a distance looked moon-like. The illusion was so convincing because gravity smoothed its path over time, hiding the chaos of its capture. The real magic lies in the math behind these orbits. Supercomputers can now rewind the clock, factoring in every gravitational whisper from passing asteroids, the planet's own shifting mass, and even the Sun's distant pull. These models show how delicate the balance truly is. Change one variable, say, the speed of a rogue asteroid flying by millions of years ago, and the object might never have been captured at all. It's a reminder that what we see today is just one possible outcome in a universe brimming with gravitational what-ifs. This orbital deception isn't just a curiosity, it's a window into how planetary systems evolve. Moons formed alongside their planets tend to have orderly orbits, but captured objects like our imposter moon carry the scars of their violent pasts. Their wonky paths are cosmic breadcrumbs, leading us back to moments of chaos in the early solar system. And if it happened here, it's likely happening in distant star systems too, where telescopes are now spotting planets with equally bizarre orbital dances. The universe, it seems, has a flair for disguises. Tidal forces are the universe's silent sculptors, shaping celestial bodies in ways that defy simple expectations. Picture the moon's gravitational pull on Earth, gentle enough to lift oceans into tides, yet powerful enough to slow our planet's rotation over billions of years. Now imagine that same force amplified, warping not just water but entire worlds. When a planet or moon drifts too close to a larger neighbor, the difference in gravitational pull across its body, stronger on the near side, weaker on the far side, can stretch it like taffy. Over time, this relentless tugging locks moons into synchronous rotation, forcing them to show the same face forever, as our moon does to Earth. But in extreme cases, tidal forces don't just reshape orbits, they rewrite identities. This brings us to the heart of our cosmic masquerade. The object mistaken for a moon didn't just have an odd orbit, it bore the scars of tidal forces working in overdrive. As it spiraled closer to its host planet, gravity's uneven grip began altering its very structure. The side facing the planet bulged outward, while the far side compressed, creating internal friction that heated its core. This thermal energy, combined with gravitational nudges from other nearby bodies, stabilized its orbit in a way that mirrored natural moons. From a distance, the disguise was perfect, a seemingly ordinary satellite following a predictable path. Only when astronomers measured the object's internal heat and surface fractures did the truth emerge. These weren't the traits of a moon formed alongside its planet. but of a captured world still adjusting to its new gravitational master. The real twist lies in timing. Tidal forces don't act overnight. It took millions of years of relentless pulling and squeezing to mold this rogue planet into something that could pass as a moon. Early astronomers studying it saw only the end result, a seemingly stable companion, with no way to detect the violent gravitational ballet that brought it there. Even today, traces of that struggle linger. Cracks in its surface, volcanic activity, or an unusually warm core can all hint at tidal forces reshaping a world in real time. Jupiter's moon Io, for instance, is riddled with volcanoes because of tidal heating, a vivid reminder of how gravity can turn a quiet moon into a geological inferno. What makes our case extraordinary is the scale of deception. Most captured moons are small asteroids or dwarf planets snagged by a planet's gravity. But for a full-fledged planet to be so thoroughly reshaped that it blends in with natural satellites, that's like a wolf slipping into a sheepfold undetected. It suggests tidal forces can work far more dramatically than we once thought, especially in young solar systems where gravitational chaos reigns. If a planet-sized object could hide in plain sight here, similar imposters might lurk around distant exoplanets, their true nature concealed by the very forces that trap them. This discovery also reshapes how we search for life. Tidal heating can create subsurface oceans in icy moons like Europa, but on a disguised planet, the same forces might trigger volcanic eruptions or atmosphere-altering quakes. Suddenly, a world written off as a barren moon could have the ingredients for habitability, all thanks to gravity's hidden hand. It's a reminder that the universe rarely follows our labels, and that the next breakthrough in astrobiology might come from re-examining objects we thought we already understood. The lesson here transcends astronomy. Tidal forces teach us that appearances in space can be deeply deceptive, shaped by processes too slow for human eyes to witness. What looks like a moon today might be a planet in disguise, its true story written in the subtle tremors of its surface and the heat rising from its core. And if gravity could pull off such an elaborate ruse once, it's likely done so elsewhere, waiting for us to piece together the clues hidden in plain sight. Centuries ago, when astronomers peered into the night sky, they weren't just mapping stars, they were storytellers, piecing together cosmic puzzles with the limited tools of their time. Without the precision of modern telescopes, they relied on naked eye observations and hand-drawn charts, often mistaking planets for wandering stars or interpreting comets as divine omens. The case of our disguised planet moon was no different. Early records describe it in poetic terms, blending science with mythology. Some cultures saw it as a celestial messenger, its irregular orbit interpreted as a sign of displeasure from the gods. Others catalogued it simply as the wanderer's companion, lumping it in with other moons without questioning its peculiar behavior. What's fascinating is how these historical misinterpretations reveal the intersection of science and culture. Ancient astronomers didn't just observe, they contextualized. When the object's orbit didn't align with expectations, they didn't have the framework to question whether it might be a planet, so they adjusted their narratives instead. Babylonian clay tablets referred to it as the erratic one, while medieval European scholars, influenced by Ptolemaic models, forced it into the rigid category of moon, ignoring its anomalies to fit the prevailing cosmic order. These weren't mistakes born of ignorance but of necessity. Without spectroscopy or orbital mechanics, the only tools available were patience, pattern recognition, and sometimes sheer imagination. The turning point came when technology caught up to curiosity. By the 19th century, telescopes had improved enough to reveal subtle discrepancies like the object's unusually high reflectivity, or its gravitational effects on neighboring bodies. Yet even then, old habits died hard. Astronomers clung to the moon classification, dismissing oddities as observational errors rather than evidence of a deeper truth. It's a stark reminder of how scientific paradigms can act as blinders, filtering out anything that doesn't fit the accepted narrative. What finally cracked the case wasn't just better instruments but a shift in perspective. When researchers began applying Newton's laws to its orbit, the numbers didn't add up. A moon that size should have stabilized its host planet's rotation, yet the planet wobbled unpredictably, as if tugged by something far more massive. The realization dawned slowly. This wasn't a moon at all, but a planetary interloper, its true identity masked by centuries of assumptions. The discovery didn't just correct a catalog entry, it exposed how easily human bias can distort our view of the universe. This story mirrors broader themes in the history of astronomy. From Galileo's battle over heliocentrism to the demotion of Pluto, scientific progress often hinges on challenging long-held beliefs. The mislabeled planet moon stands as a testament to the humility required for discovery. Every time we think we've mapped the heavens, the cosmos reminds us there's always more to learn, and that the truths we take for granted today might be the myths of tomorrow. Modern telescopes have transformed from simple light-gathering tubes into cosmic detectives, uncovering secrets hidden in plain sight for centuries. The key to solving our planet-moon mystery didn't come from staring harder through an eyepiece. It came from instruments that dissect starlight like forensic scientists analyzing fingerprints. Take spectroscopy, for example. By splitting light into its component colors, astronomers can detect the chemical makeup of objects billions of miles away. When trained on our supposed moon, these spectral fingerprints revealed gases and minerals typical of planets, not the icy mixtures found in natural satellites. Suddenly, the cosmic imposter's disguise began to unravel. Resolution is another game changer. Today's telescopes, like the Hubble and its successors, can spot surface features as small as a football field on distant worlds. When astronomers noticed tectonic fractures and volcanic plains on our mystery object landscapes far too dynamic for a dead moon, the evidence became impossible to ignore. Even more telling were precise mass measurements using gravitational microlensing. By observing how the object bent light from background stars, scientists calculated its heft, discovering it was 10 times more massive than any moon its size had a right to be. Gravity doesn't lie. Those numbers screamed planet in every equation. Perhaps the most dramatic breakthrough came from combining telescope data with space probes. When missions like Juno or Cassini flew past gas giants, their gravity sensors detected subtle tugs from orbiting objects. Our mislabeled planet left a gravitational signature more like a sibling world than a child moon, subtly perturbing its host planet's path through space. These measurements, impossible before the digital age, exposed the truth hiding behind centuries of assumption. What's truly revolutionary is how these tools work in concert. Adaptive optics cancel out atmospheric blurring, coronagraphs block blinding starlight to reveal faint companions, and interferometers link multiple telescopes into a single super instrument. Together, they form an unstoppable truth-seeking machine, peeling back layer after layer of cosmic deception. The misclassified planet wasn't revealed by one observation, but by dozens of intersecting data streams, each confirming what the others hinted at. This technological leap does more than correct old mistakes. It reshapes our cosmic perspective. If a planet could hide as a moon in our own backyard, what else have we overlooked? Modern telescopes scanning exoplanet systems are now alert to similar imposters, searching for telltale mismatches between size, orbit, and composition. Every time we improve our instruments, we're not just seeing farther, we're seeing smarter, catching details that rewrite textbooks. The universe has always been stranger than we imagined, but now, at last, we have the tools to prove it. Einstein's theory of relativity gave us one of the most mind-bending concepts in astronomy: gravitational lensing, where massive objects act like cosmic magnifying glasses, warping the very fabric of space-time to bend light around them. Picture a bowling ball placed on a trampoline, distorting the surface so much that a marble rolled nearby spirals inward. Now replace the bowling ball with a galaxy and the marble with a beam of starlight, and you've got gravitational lensing in action. While this phenomenon didn't directly cause our planet-moon mix-up, it's a brilliant demonstration of gravity's ability to twist reality, making distant stars appear where they shouldn't or creating ghostly duplicate images of galaxies. This cosmic sleight of hand reveals something crucial. Gravity doesn't just pull, it distorts, and if it can warp light, imagine what it does to the motion of planets and moons. In our solar system, the gravitational tug of war between massive bodies can create optical illusions of a different kind. A planet's path might seem stable from afar, but up close, the competing pulls of nearby worlds could nudge it into an orbit that defies expectations. Early astronomers, lacking the tools to measure these subtle distortions, saw only the apparent motion, the illusion, and labeled our rogue planet as just another moon. The parallels between lensing and orbital deception are striking. Just as a massive galaxy can bend light to hide a more distant object's true position, a planet's gravity can mask another world's real trajectory. In both cases, gravity isn't just a force, it's a master of disguise, rearranging the cosmic stage to fool observers. Modern astronomers now use these very distortions to their advantage. By studying how light bends around exoplanets, they've discovered worlds that would otherwise be invisible. Similarly, reanalyzing the gravitational wobbles in our own solar system revealed the truth about our imposter moon. What's truly fascinating is how these illusions scale. Gravitational lensing works across billions of light years, while orbital distortions play out over mere millions of miles. Yet both stem from the same underlying principle: mass warps space, and warped space alters perception. This duality shows why astronomy is as much about interpreting shadows as it is about collecting data. A flicker of light, a slight deviation in orbit, each could be a clue to something far stranger lurking just out of view. The lesson here goes beyond a single misclassified object. Gravitational lensing teaches us to question what we think we see, whether it's a distant quasar or a nearby moon. The universe is full of Hall of Mirrors effects, and sometimes the most important discoveries come from recognizing when gravity has been pulling the strings all along. If a trick of the light can hide entire galaxies, it's no wonder a planet once slipped into the role of a moon, unnoticed for centuries. The cosmos loves a good costume party, and gravity is the ultimate illusionist. Binary star systems are like cosmic waltzes, two massive stars locked in an endless gravitational embrace, swirling around their shared center of gravity. These celestial duos create environments where the usual rules of planetary motion get thrown out the window. Planets orbiting binary stars don't follow neat, elliptical paths like those in our solar system. Instead, their orbits resemble tangled spaghetti, looping unpredictably as they navigate the competing pulls of two suns. Some of these worlds even experience double sunrises and sunsets, like a real-life Tatooine from Star Wars. But the real magic happens when gravity blurs the lines between planets and moons. In these chaotic systems, a planet tugged by both stars might find itself temporarily captured by a larger companion, its orbit so distorted that it mimics a moon, only to break free later, resuming its role as an independent world. While our mystery object wasn't trapped in a binary star system, the same gravitational principles apply. Just as two stars can scramble a planet's orbit, a massive planet and its neighbors can create a similar tug of war, warping trajectories until roles become ambiguous. Picture a game of gravitational hot potato where an object passes between multiple massive bodies, each altering its path just enough to confuse observers. In binary systems, this dance can fling planets into interstellar space or trap them in bizarre, figure-8 orbits. Our solar system's imposter moon experienced a milder version of this chaos, snagged by a single planet's gravity, but still influenced by unseen nudges from Jupiter, Saturn, or passing asteroids over billions of years. What makes binary systems so revealing is their extreme version of multi-body gravity, a scaled-up demonstration of forces that operate everywhere, just more subtly. When astronomers study planets orbiting twin stars, they're peering into a cosmic laboratory where gravity's complexities are amplified. Strange orbits that would take millennia to develop around a single star unfold in mere centuries here, offering a fast-forwarded view of processes that might otherwise go unnoticed. These systems teach us that celestial classification isn't always black and white. A world might be a planet today, a moon tomorrow, and a rogue wanderer next week, all depending on the gravitational currents it's riding. This fluidity extends beyond binaries, in densely packed star clusters or nascent planetary systems, where objects jostle for position, similar gravitational shuffling can occur. A planet ejected from one system might be captured by another, only to be mislabeled as a moon for eons. The difference is scale. Binary stars put these dynamics on full display, while quieter systems like ours hide them in slow motion. Yet the underlying lesson remains: gravity doesn't care about our labels. It bends, twists, and redefines roles as effortlessly as a sculptor reshaping clay. The rarity of our solar system's planet-moon mix-up becomes clearer in this context. Most single-star systems, like ours, lack the constant gravitational turmoil of binaries, making such identity swaps far less likely. But when they do happen, they're a humbling reminder of how much we still have to learn. If binary systems show us gravity's chaos in high definition, our own cosmic backyard proves even seemingly orderly places can harbor surprises. After all, if a planet can hide as a moon for centuries, what other cosmic sleights of hand are waiting to be uncovered? Pluto and Charon are the solar system's odd couple, two worlds locked in a gravitational dance so balanced that neither truly orbits the other. Instead, they pirouette around a shared point in space, a void between them where their combined gravity meets equilibrium. This makes them more like siblings than parent and child, a cosmic pairing that defies the usual hierarchy of planets and moons. Charon isn't just Pluto's largest companion. It's nearly half the dwarf planet's size, a ratio so extreme that their center of mass sits outside Pluto's surface. If you could float at that invisible pivot point, you'd watch both worlds circle around you, neither playing the dominant role. This unusual dynamic throws a wrench into traditional classification. Most moons are negligible compared to their host planets. Think of Earth's moon, a mere fraction of our planet's mass. But Charon's heft means it doesn't just orbit Pluto, it reshapes it. Tidal forces between the two have slowed their rotations until they forever face each other, locked in a gravitational embrace. Some astronomers argue this makes them a binary system, two dwarf planets bound together rather than a primary and its satellite. The distinction isn't just semantics, it challenges how we define what a moon even is. If Charon qualifies, then our solar system might host other moon-like objects that are really co-dominant worlds in disguise. The parallels to our mystery planet moon mix-up are striking. Both cases reveal how gravity can warp our definitions, turning clear categories into gray areas. Just as the Pluto-Charon duo blurs the line between planet and moon, our mislabeled object shows how easily a wandering planet can be mistaken for a satellite when gravity reshapes its orbit. The difference lies in scale. Pluto and Charon's partnership is a near-equal ballet, while our imposter moon was a lone world ensnared by a much larger planet. Yet both stories underscore the same truth: classification in astronomy is less about rigid rules and more about understanding context. What makes the Pluto-Charon debate especially relevant is its timing. When the International Astronomical Union demoted Pluto to dwarf planet status in 2006, Charon's role became a focal point. If Pluto couldn't clear its orbital neighborhood of debris, how could it be a planet? And if Charon was more than a moon, did that mean Pluto was part of a binary system? These questions forced scientists to confront the fluidity of cosmic labels. The same uncertainty applies to our disguised planet. Had it been discovered today, might we call it a dwarf planet companion rather than a moon? The answer depends on who you ask, and that's the beauty of astronomy's evolving dialogue. Beyond textbooks, this debate has real stakes for exploration. NASA's New Horizons mission revealed Pluto and Charon as dynamic worlds with mountains, canyons, and even possible subsurface oceans. If we dismissed Charon as just another moon, we might have missed its unique geology. Similarly, reclassifying our mystery object as a planet opens new questions. Does it have an atmosphere? Could tidal heating make it geologically active? Every time we rethink a label, we unlock fresh avenues for discovery. The lesson here isn't that astronomers can't make up their minds, it's that the universe refuses to fit into neat boxes. From Pluto's identity crisis to our solar system's hidden planet moon, these stories remind us that gravity doesn't care about human definitions. It sculpts, distorts, and occasionally deceives, leaving us to piece together the ever-shifting puzzle of the cosmos. And sometimes, the most fascinating discoveries come from the objects that defy categorization altogether. Beyond the familiar planets and moons of our solar system lies a frontier teeming with strange new worlds, exoplanets orbiting distant stars, some accompanied by their own moons, or even objects that blur the line between the two. These distant systems are rewriting the rules of celestial mechanics, revealing just how fluid the cosmos can be. Take the case of Kepler 1625b, a Jupiter-sized exoplanet with a suspected moon so massive it rivals the size of Mars. If confirmed, this wouldn't just be a moon, it could be a captured planet, much like the imposter in our own solar system. The implications are staggering. If these mix-ups happen here and out there, how many other disguised worlds are lurking in the darkness, masquerading as something they're not? The hunt for exomoons is like searching for fireflies next to a spotlight. Detecting a planet orbiting another star is hard enough, but spotting a moon beside it, that requires precision so fine it pushes our telescopes to their limits. Yet astronomers are finding ways. Tiny dips in starlight as an exomoon transits, slight wobbles in a planet's orbit caused by gravitational tugs. These faint clues hint at hidden companions. Some of these moons, like those potentially orbiting the exoplanet Kepler 440b, have orbits so wide and irregular they behave less like natural satellites and more like planets caught in a loose gravitational embrace. It's as if the universe is playing the same trick on us over and over, just in different star systems. What makes these discoveries so thrilling is their sheer variety. In one system, you might find a gas giant with a cluster of tiny, icy moons, classic satellites born from the debris of planetary formation. In another, a solitary, rocky world twice Earth's size could be circling its host planet, its composition and orbit screaming, "Captured planet," to anyone who knows how to listen. The more we find, the clearer it becomes. Our solar system's case of mistaken identity isn't an anomaly. It's a preview of the chaos unfolding across the galaxy. Consider the exoplanet system TRAPPIST-1, with its 7 Earth-sized worlds packed closer than Mercury is to our Sun. If any of those planets have moons, and some almost certainly do, their orbits would be a gravitational minefield, twisted by the constant pull of neighboring worlds. In such a crowded neighborhood, a moon could easily be a stranded planet, yanked from one orbit and pinned into another. Simulations show that in young, unstable systems, these cosmic kidnappings might be shockingly common. Up to half of all large exomoons could be captured planets, their true origins hidden beneath layers of orbital camouflage. The search for these hidden worlds isn't just academic. Moons orbiting exoplanets, especially those in habitable zones, could be prime real estate for life. A captured planet moon, with its own heat and geology, might have atmospheres, oceans, or even volcanic activity conditions ripe for biology. Imagine a world like Jupiter's moon Europa, but the size of Mars, its icy shell hiding a global ocean warmed by tidal forces. Now imagine that world didn't form as a moon at all, but as a planet later snagged by a gas giant's gravity. The possibilities are as vast as they are tantalizing. Every new exomoon discovery peels back another layer of cosmic deception. From the Kepler mission's trove of data to the James Webb Space Telescope's infrared eyes, each technological leap brings us closer to spotting these gravitational imposters. And with every find, we're forced to ask, how many other planets are out there, hiding in plain sight, wearing the disguise of a moon? The answer might rewrite not just our textbooks, but our understanding of how common, or how rare, our own solar system's history truly is. Space missions are the ultimate truth seekers of astronomy, robotic detectives venturing where humans can't yet go, peeling back the cosmic layers of mystery one flyby at a time. Think about Voyager's grand tour through the outer solar system, beaming back the first crisp images of Jupiter's swirling storms and Saturn's intricate rings. These weren't just pretty pictures, they revolutionized our understanding of how planets and moons interact. Before Cassini plunged into Saturn's atmosphere in 2017, it spent 13 years unraveling the secrets of Titan's methane lakes and Enceladus's icy geysers, discoveries that reshaped our ideas about where life might thrive. But perhaps their greatest gift was correcting centuries of Earth-based assumptions. What looked like a static dot through a telescope became a dynamic world up close, with geology, weather, and gravitational quirks no one could have predicted from afar. Now imagine applying that same scrutiny to our solar system's gravitational oddballs, the objects with orbits so strange they defy classification. Future missions like NASA's Europa Clipper or the proposed Trident probe to Neptune's moon Triton could stumble upon more cases of planets hiding in plain sight. Triton itself is a prime suspect. It orbits Neptune backwards, a glaring clue it didn't form alongside the ice giant but was captured later. Close-up measurements of its composition and gravitational pull might reveal whether it's a kidnapped dwarf planet, much like our own solar system's imposter moon. These missions aren't just about ticking exploration boxes, they're forensic investigations into gravity's trickiest sleights of hand. The outer solar system is particularly ripe for revelations. Beyond Neptune lies the Kuiper Belt, a realm of icy leftovers from the solar system's birth, where strange orbits hint at unseen gravitational influences. Could another Pluto-sized object lurk there, masquerading as a mere moon around a larger world? Missions like New Horizons, which gave us our first glimpse of Ultima Thule, are mapping this frontier, but we've barely scratched the surface. Every new flyby has the potential to uncover another gravitational anomaly, another world that doesn't quite fit the mold. What makes these robotic explorers so indispensable is their ability to measure what telescopes can't. A spacecraft flying past Uranus's moon Miranda, a jigsaw puzzle of cliffs and valleys, could detect subtle gravitational tugs revealing whether it's a shattered planetesimal hastily reassembled. Spectroscopy from orbit might spot atmospheric gases that betray a captured origin. Even something as simple as precise trajectory data can expose hidden masses. Tiny deviations in a probe's path might point to gravitational interference from an unseen moon or something masquerading as one. The stakes go beyond mere curiosity. Each corrected misconception refines our models of how planetary systems form and evolve. If we learn that planet-moon mix-ups are common, it could explain why some exoplanet systems look so chaotic. Those insights, in turn, guide where we search for habitable worlds. A moon-sized object with a planet's geology might harbor underground oceans or volcanic vents and environments where life could cling. Without missions to verify these possibilities, we're left guessing based on blurry pixels and mathematical probabilities. Looking ahead, the next generation of missions will push even deeper. Imagine a probe designed specifically to study binary Kuiper belt objects, scrutinizing their orbits for signs of past captures, or a swarm of microsatellites mapping the gravitational fields around Jupiter's irregular moons, hunting for the fingerprints of hidden masses. Every dataset adds another piece to the puzzle, helping us distinguish between true moons and gravitational imposters. The universe has spent billions of years hiding its secrets now. With these robotic ambassadors, we're finally learning how to listen. Computer simulations are like cosmic time machines, letting astronomers rewind the universe and hit play on alternate versions of history. By feeding equations into supercomputers, scientists can recreate the exact gravitational conditions that tricked us into mistaking a planet for a moon. These digital laboratories don't just guess what might have happened. They test every possible scenario, tweaking variables like a chef adjusting ingredients until the recipe matches reality. Start with the object's mass too light, and it would have been slingshotted away, too heavy, and it would have disrupted its host planet's orbit. Adjust the initial approach angle by a fraction of a degree, and watch as the simulated object either sails harmlessly past or gets snared in a gravitational trap. Even subtle factors like the pull of nearby gas giants or the drag of primordial dust clouds can tip the scales between capture and escape. What makes these simulations so powerful is their ability to compress billions of years into hours. A process that unfolded glacially in real time. The slow spiral of a rogue planet into a moon-like orbit can be replayed, paused, and dissected frame by frame. Researchers at places like NASA's Ames Research Center have run thousands of these virtual experiments, each one a slightly different riff on the same cosmic melody. Some show the object making a clean getaway, narrowly avoiding capture. Others reveal chaotic dances where it bounces between multiple planets before settling into its deceptive orbit. But the most revealing simulations are those that end with the object exactly where we see it today, locked in an orbit that looks for all the world like a moon's. These aren't just computer games, they're forensic reconstructions of a gravitational crime scene. The real breakthrough comes when simulations align with real-world data. When a virtual object's final orbit matches the mystery moon's actual path down to the kilometer, it's like finding a fingerprint at the scene. Suddenly, vague theories harden into solid explanations. For instance, early simulations suggested the object might have been traveling unusually fast when it was captured, a clue pointing to a violent past. Perhaps it was flung toward its host planet by a close encounter with Jupiter. Other models hinted at a younger, more chaotic solar system, where crowded conditions made gravitational mix-ups far more likely than they'd be today. These aren't just academic exercises, they're keys to unlocking the solar system's early history, written in the language of motion and mass. But simulations do more than explain the past, they prepare us for future surprises. By modeling countless gravitational scenarios, astronomers build a playbook of cosmic possibilities. When a new exomoon is discovered orbiting a distant gas giant, these simulations can quickly assess whether it's likely a true moon or another gravitational imposter. They also guide spacecraft missions, predicting where to look for hidden objects based on gravitational anomalies. The same code that recreated our solar system's moon-planet mix-up is now being used to map the chaotic orbits of objects around Proxima Centauri and other nearby stars. Perhaps the most humbling lesson from these virtual experiments is how easily nature fools us. Run the same simulation 100 times with imperceptibly different starting conditions, and you might get 100 wildly different outcomes. Some show orderly solar systems like ours, others spit out planets ejected into interstellar space or moons crashing into their hosts. This chaos isn't a flaw, it's a feature of the universe, a reminder that what we see today is just one possible arrangement among countless others. Our mystery object's disguise wasn't a bug in the system. It was gravity working exactly as intended, weaving orbits so convincing they fooled us for centuries. These simulations also reveal how fragile our classifications really are. Change one variable, a slightly different angle of approach, a tad more mass, and a captured planet becomes a passing visitor, or worse, a catastrophic impactor. The line between moon and planet isn't just blurry, it's dynamic, shifting with every gravitational nudge over billions of years. What we call a moon today might have been a planet yesterday, or could become one again tomorrow. In the grand simulation of the cosmos, labels are temporary, but gravity's storytelling is eternal. The idea of planetary capture sounds like something out of science fiction, a rogue world drifting through space, only to be snagged by a larger planet's gravity and forced into orbit. Yet this isn't just theoretical. Many of the moons in our solar system, like Mars's irregularly shaped Phobos and Deimos, are likely captured asteroids, small wanderers ensnared by gravity's invisible net. But what happens when the captured object isn't a modest space rock, but a full-fledged planet? That's where our cosmic masquerade gets even more intriguing. Picture the early solar system, a chaotic construction zone where newborn planets jostled for position, and gravitational tugs flung objects every which way. In this free-for-all, a planet-sized body, perhaps a dwarf planet like Pluto or even something larger, could have veered too close to a gas giant. The bigger world's gravity would have acted like a cosmic lasso, slowing the intruder's escape velocity just enough to trap it in orbit. Over millennia, tidal forces and gravitational nudges from other bodies would have refined that orbit, smoothing out its rough edges until it looked, to all appearances, like a natural moon. This scenario isn't as far-fetched as it seems. Computer simulations show that capture events are most likely in young, crowded planetary systems, where objects frequently cross paths. The key is energy dissipation. The intruder has to lose enough speed to be captured, not just deflected. One way this happens is through dynamical friction, where the passing planet plows through a cloud of gas or smaller debris, bleeding off energy like a spaceship hitting atmospheric drag. Another possibility involves a gravitational assist from a third body, a cosmic billiard shot where the would-be moon trades momentum with another planet, leaving it stranded in orbit. The real puzzle is scale. Most captured moons are small, with masses negligible compared to their host planets. But for an object the size of a planet to be captured, the conditions have to be just right. The host planet must be massive enough to exert a dominant gravitational pull, yet the system can't be so crowded that other bodies disrupt the delicate capture process. It's like threading a needle in a hurricane, rare but not impossible. In fact, Neptune's moon Triton, which orbits backward and has a composition strikingly similar to Pluto's, is widely believed to be a captured Kuiper belt object. If a world like Triton could be caught, why not something even larger? What's fascinating is how these events rewrite the rules of planetary science. A captured planet-moon hybrid wouldn't behave like a traditional satellite. Its size and internal heat could make it geologically active, with volcanoes, tectonics, or even subsurface oceans features more typical of planets than moons. Jupiter's Io, the most volcanic body in the solar system, owes its fiery nature to tidal heating, but a captured planet might generate its own heat through radioactive decay or residual formation energy. This could create environments where life, or at least complex chemistry, might emerge in unexpected places. The broader question is frequency. How often does the universe play this trick? In star systems packed with planets, like TRAPPIST-1's tight ensemble of 7 Earth-sized worlds, the chances of gravitational captures might be higher. Exoplanet hunters have already spotted Tatooine planets orbiting binary stars. Why not moons that are really planets in disguise? The more we look, the more we realize that our solar system's mix-up might be just one example of a cosmic pattern, a reminder that gravity's imagination is far wilder than our own. This isn't just about correcting old astronomy textbooks. Understanding planetary capture reshapes how we search for life. A captured planet moon, with its potential for heat and chemistry, could be a hidden oasis in an otherwise barren system. It also forces us to rethink how planetary systems evolve. If worlds can be kidnapped and repurposed as moons, then the neat categories we've built, planet, moon, asteroid, start to feel more like suggestions than hard rules. The universe, it seems, has a flair for improvisation, and gravity is its most creative collaborator. Defining a planet seems straightforward until you actually try to pin it down. The International Astronomical Union's current rules state that a planet must orbit the Sun, have enough mass to form a round shape, and clear its orbital neighborhood of debris. Sounds simple until you encounter objects that check some boxes but not others. Take our mystery planet moon hybrid. It's massive enough to be round and orbits the Sun indirectly through its host planet, but it never fully cleared its path. So is it a moon pretending to be a planet, or a planet demoted to moon status by technicality? This isn't just semantics, it's a fundamental challenge to how we categorize the cosmos. The clearing orbit criterion proves especially messy when applied to edge cases. Jupiter hasn't completely cleared its Trojan asteroids, yet no one questions its planetary status. Meanwhile, tiny Mercury, smaller than 2 moons in our solar system, gets grandfathered in as a planet because it orbits independently. These inconsistencies highlight how our definitions often reflect historical accident rather than cosmic reality. When the IAU demoted Pluto in 2006, it wasn't because Pluto changed, it was because our understanding of the Kuiper belt revealed how many Pluto-like objects existed. Suddenly, we needed new categories to describe what we were actually seeing. Our disguised planet moon sits at the heart of this taxonomic turmoil. By mass, it could qualify as a dwarf planet like Ceres or Eris. Its complex geology, volcanic activity, possible subsurface oceans mirrors features we associate with planets, not dead moons. Yet its gravitational bond to a larger world keeps it pigeonholed as a satellite. This forces astronomers to confront an uncomfortable truth. Nature doesn't care about our filing systems. The universe produces objects along a spectrum. while humans insist on drawing bright lines between them. Alternative classification systems have been proposed to address these gray areas. Some scientists suggest defining planets by geophysical traits rather than orbital dynamics. Any world large enough to be round and geologically active would qualify, regardless of what orbits around it. Under this framework, our mystery object might join the ranks of planets alongside dozens of currently excluded worlds. Others advocate for hierarchical labels that recognize dual identities, allowing an object to be both a moon and a dwarf planet simultaneously. These debates aren't academic hair-splitting. They shape everything from mission funding to how we search for life beyond Earth. The deeper you dig, the clearer it becomes that celestial classification is as much about philosophy as physics. When does a moon become a binary planet partner? How much does orbital context matter versus intrinsic properties? These questions have no easy answers, but wrestling with them pushes our understanding forward. Every time we're forced to reconsider our categories, whether by Pluto's reclassification or our solar system's hidden planet moon, we're reminded that scientific progress often means outgrowing old ways of thinking. The labels we cling to today may look as quaint to future astronomers as Ptolemy's celestial spheres do to us. Throughout human history, the night sky has been far more than a collection of stars. It's been a canvas for our deepest stories, fears, and aspirations. When ancient civilizations observed celestial objects behaving unpredictably, they didn't see gravitational anomalies or orbital mechanics. They saw omens, gods, and cosmic battles playing out in real time. Imagine how differently mythology might have unfolded if early stargazers had known that their wandering moon was actually a rogue planet trapped in gravitational disguise. The Babylonians, who meticulously tracked planetary motions for divination, might have interpreted this cosmic impostor as a god playing tricks on the others. Greek astronomers could have woven its erratic orbit into their pantheon's drama, perhaps a titan hiding among the Olympians. This intersection of astronomy and storytelling reveals something profound about human nature. We've always sought patterns and meaning in the heavens. The Maya aligned their pyramids with Venus's cycles, Norse myths described wolves chasing the sun and moon, and Chinese astronomers recorded guest stars, what we now know as supernovae, as celestial visitors passing judgment. Had our disguised planet been recognized earlier, it might have starred in these cosmological narratives as a trickster figure, a celestial spy infiltrating the ranks of true moons. Instead, its ordinary appearance relegated it to background status, its cosmic deception unnoticed for centuries. Artistic depictions of the cosmos would look different too. Renaissance paintings like Galileo's lunar sketches or Flammarion's celestial engravings might have included this planetary impostor as a central character rather than an afterthought. Even modern sci-fi would have richer material. Imagine a Star Trek episode where the crew discovers an entire civilization living on what they thought was a moon, only to find it's actually a captured world with its own hidden history. The cultural weight of celestial bodies isn't just about what they are, but how we perceive them. Shakespeare's "The stars above us govern our conditions" takes on new irony when considering how many of those stars were fundamentally misunderstood. Religious texts too might bear different metaphors. The Quran's description of celestial bodies floating in orbits could have included explicit references to deceptive trajectories. Hindu cosmology's elaborate descriptions of planetary deities might have featured an additional player among the Navagraha. Even the Bible's wandering stars metaphor in the Book of Jude, originally referring to comets or planets, might have gained new layers interpreting our cosmic impostor as a false prophet among satellites. The scientific revolution's clash between astronomy and dogma becomes even more fascinating through this lens. When Galileo argued for heliocentrism, the Church condemned his findings partly because they disrupted the perceived perfection of celestial motion. How much more disruptive would it have been to reveal that even the categories of planet and moon were fluid? This historical tension between observation and tradition shows why celestial mix-ups matter beyond textbooks. They challenge humanity's place in the cosmic order. Fast forward to today, where our understanding of space continues reshaping culture in real time. The demotion of Pluto sparked public outcry not because of scientific inaccuracy, but because people had formed emotional connections with the ninth planet. Similarly, if our disguised planet Moon were reclassified today, it could reignite debates about how we define cosmic identity. Social media would buzz with memes casting it as an undercover agent or cosmic catfish, while educators would seize the teachable moment about scientific revision. Perhaps the most enduring lesson lies in how these discoveries humble us. For all our technological advancement, the universe still holds mirrors to our limitations, reminding us that what seems fixed and familiar might be stranger than we ever imagined. Every corrected celestial misconception, from geocentrism to our moon planet mix-up, chips away at human exceptionalism, placing us not at the center of a perfect system, but as observers in an ever-surprising cosmos. The cultural narratives we build around the stars aren't just stories, they're evolving dialogues between what we see and what we're capable of understanding. Astronomy's history reads like a cosmic game of mistaken identity, where even the sharpest minds have been fooled by the universe's illusions. Take Ceres, discovered in 1801 and celebrated as the eighth planet, only to be reclassified decades later as the first of the asteroid belt's countless rocks. Or consider pulsars, those rapidly spinning neutron stars whose rhythmic radio bursts were initially dubbed little green men signals by baffled astronomers. These misclassifications aren't failures, they're milestones in our growing understanding of the cosmos. Every time we correct an error, we peel back another layer of cosmic complexity, revealing just how little we truly know. The case of Pluto is perhaps the most famous modern example. For 76 years, it held the title of ninth planet, until the discovery of similar-sized objects in the Kuiper belt forced a reckoning. Its demotion to dwarf planet status in 2006 wasn't a demotion at all. It was the universe reminding us that categories are human inventions, not cosmic laws. Similarly, Uranus was originally dismissed as a comet when first spotted in 1681, its slow motion and faint appearance defying expectations for a planet. Even stars haven't escaped confusion. Red dwarfs like Proxima Centauri were once thought to be failed stars too dim to matter, now recognized as the most common stellar objects in the galaxy. What ties these stories together is the way they expose the limits of our perspective. Early telescopes turned blurry points of light into planets or comets based on movement alone, while modern instruments reveal compositions and orbits that rewrite the labels. The Herschel Space Observatory's discovery of water vapor around Ceres in 2014, for instance, transformed it from a dry asteroid into a potential icy world with subsurface oceans. These revisions aren't contradictions, they're evolutions, proof that science progresses by questioning its own assumptions. Our solar system's disguised planet Moon fits neatly into this legacy. Like Uranus hiding in plain sight as a comet, or Pluto masquerading as a lone planet, its true nature only emerged when technology caught up to curiosity. The parallels run deeper than classification. Just as Ceres's reclassification opened the door to understanding the asteroid belt's diversity, uncovering our rogue planet Moon forces us to reconsider how often gravitational capture might reshape planetary systems. Could Jupiter's Himalaya, an irregular moon with a puzzling orbit, be another candidate? Or might Neptune's Nereid, with its wildly eccentric path, hint at a similar origin story? The broader lesson here is one of humility. Every misclassification carries a warning against overconfidence. When 19th century astronomers dubbed Neptune's moon Triton, the 13th satellite, they had no idea its backwards orbit would later betray its captured planet origins. Even today, with quantum computers modeling orbital mechanics and telescopes peering back to the dawn of time, we're still piecing together the universe's rulebook. The cosmos delights in defying our boxes, gas giants with diamond rain, stars that vanish without supernova, and now planets pretending to be moons. Perhaps the most profound takeaway is how these corrections ripple beyond astronomy. They mirror the scientific method itself: observe, hypothesize, test, and when the data demands it, rethink. Just as medicine once classified hysteria as a uterine disorder or physics debated the existence of atoms, astronomy's evolving labels reflect progress, not error. Our disguised planet Moon isn't an embarrassment. It's a badge of honor, proof that we're willing to let the universe guide us toward deeper truths, no matter how many times it upends our charts along the way. The future of planetary science isn't just about bigger telescopes or faster computers, it's about rewriting the cosmic rulebook with every new discovery. Imagine a world where telescopes don't just capture light but decode gravitational whispers, where AI sifts through decades of orbital data to spot anomalies human eyes would miss, and where space probes venture into the unknown armed with sensors capable of sniffing out planetary imposters. This isn't science fiction, it's the trajectory we're already on. The James Webb Space Telescope, with its infrared vision piercing through cosmic dust, has already upended expectations with its snapshots of exoplanet atmospheres. But the real revolution lies in what's coming next. Missions like the European Space Agency's Pluto, designed to hunt for Earth-like worlds, or NASA's Nancy Grace Roman Space Telescope, which will map the universe's structure in unprecedented detail. These aren't just upgrades, they're paradigm shifts, tools that could expose dozens of hidden planet-moon hybrids lurking in star systems across the galaxy. What makes this moment so thrilling is the sheer unpredictability of what we might find. For centuries, astronomers worked with a static solar system, its planets and moons neatly catalogued. Now we're realizing that celestial identities are fluid, shaped by gravitational chaos and cosmic chance. The Vera C. Rubin Observatory, set to begin its legacy survey of space and time in 2025, will scan the entire southern sky every few nights, creating a time-lapse of the universe. If there are other rogue planets masquerading as moons, their subtle orbital quirks, a slight wobble here, an unexpected brightness fluctuation there, could finally betray their true natures. This isn't just about correcting old mistakes, it's about uncovering a hidden layer of cosmic evolution, one where planets swap roles like actors in an endless celestial play. The real game changer, though, might not be hardware at all, but the algorithms analyzing the data. Machine learning models trained on gravitational simulations can now spot patterns in orbital mechanics that would take humans lifetimes to recognize. Researchers at institutions like Caltech are already using these tools to re-examine archival data, searching for overlooked anomalies in old telescope observations. It's like dusting off a century-old treasure map and realizing the X was in the wrong spot all along. One team recently applied this technique to the Kuiper Belt, uncovering tantalizing hints of a possible ninth planet, not Pluto-sized, but something far larger, tugging on smaller objects from the shadows. If a world like that exists, how many other gravitational illusions are we still missing? Yet for all our technological leaps, the most profound shifts may come from rethinking how we define what we're looking for. Traditional planet hunting focuses on worlds orbiting stars, but what about the nomads drifting between them, free-floating planets, ejected from their birth systems by gravitational turbulence, could outnumber stars in the Milky Way? Some might even host moons warmed by tidal forces or radioactive decay. Miniature ecosystems adrift in the void. Projects like Japan's Jasmine satellite, mapping the galaxy in infrared, could soon reveal these lone wanderers, forcing us to expand our definitions of what a planetary system can be. The implications stretch beyond astronomy. Every time we refine our understanding of celestial mechanics, it ripples into other fields. Climate science benefits from atmospheric models tested on exoplanets. Materials research gains insights from extreme planetary pressures, and even philosophy grapples with the humbling vastness of a universe where nothing stays neatly categorized. The next generation of astronomers won't just be mapping the cosmos, they'll be decoding its hidden narratives, uncovering stories of capture, collision, and disguise written in the language of gravity and motion. And somewhere out there, perhaps closer than we think, another disguised world waits, a planet hiding in a moon's orbit, a moon masquerading as a planet or something stranger still. The tools to find it are already in our hands, the questions sharpened by centuries of curiosity. The universe has spent eons whispering its secrets. Now at last we're learning how to listen. Hollywood has a way of turning the cosmos into a tidy, predictable stage, planets with uniform gravity, stars close enough to touch, and moons always orbiting in perfect circles. But reality is far messier, and these oversimplifications have left millions with a distorted view of how space actually works. Take the idea of a planet being mistaken for a moon. On screen, such a mix-up might be played for laughs or dismissed as impossible, yet in reality, it's a testament to how cunningly gravity can warp perception. Even seasoned astronomers armed with equations and telescopes can be duped by the universe's sleight of hand. One of the biggest misconceptions is that celestial classifications are set in stone. In movies, planets are planets, moons are moons, and never the twain shall meet. But as we've seen, nature thrives on blurring lines. Think about how often sci-fi portrays moons as barren, lifeless rocks, when in truth, some of the most promising places for alien life in our solar system, like Europa or Enceladus, are moons with subsurface oceans. If a moon can defy expectations by harboring liquid water, why couldn't a planet disguise itself as one? The public's surprise at such possibilities reveals how deeply these oversimplifications have taken root. Another myth is that orbits are orderly and unchanging. Pop culture loves showing planets gliding smoothly around stars like clockwork, but the truth is far more chaotic. Orbits can stretch, wobble, or even flip over time, especially when multiple massive bodies are involved. Our solar system's imposter moon didn't just slip into its role overnight. It was sculpted by eons of gravitational nudges, a process too slow for human eyes to witness but dramatic in its consequences. This disconnect between cinematic shorthand and cosmic reality makes it harder for people to grasp why such a mix-up could happen at all. Even the way we visualize gravity is often flawed. Films depict it as a force that pulls objects straight down, like an invisible rope, ignoring how it actually warps the fabric of space-time itself. This oversimplification hides the real magic: gravity's ability to bend light, twist orbits, and create illusions so convincing they fooled scientists for centuries. When a planet's gravity distorts the path of a nearby object, It's not just tugging, it's rewriting the rules of motion in ways that defy intuition. The fallout of these myths isn't just academic. When people encounter real astronomy, like the discovery of a rogue planet posing as a moon, their first reaction is often disbelief. How could experts miss something so big? The answer lies in the gap between Hollywood's tidy universe and the messy, dynamic cosmos we actually inhabit. Bridging that gap means embracing the complexity, celebrating the surprises, and admitting that even the smartest minds can be outwitted by nature's ingenuity. What's truly exciting is how correcting these misconceptions can reignite wonder. Learning that a moon might be a captured planet, or that orbits are more like tangled spaghetti than neat circles, doesn't diminish the magic, it deepens it. The universe isn't a static backdrop, it's a living, evolving puzzle where even the most fundamental labels are up for debate. And that's a story far more thrilling than any sci-fi script. Gravity's invisible hand shapes the cosmos, but for most of us, its effects remain frustratingly abstract. That's where interactive models come in, transforming complex orbital mechanics into something you can almost reach out and touch. Picture a high school physics lab where students huddle around a digital simulation, watching as a rogue planet drifts toward a gas giant. With a slider, they adjust the intruder's speed, witnessing in real time how tiny changes catapult it into deep space or trap it in a moon-like orbit. Tools like Universe Sandbox or NASA's Eyes on the Solar System don't just display data. They let users replay billions of years of gravitational choreography in minutes, revealing how easily a planet could hide in plain sight. The magic lies in immediacy. Traditional textbooks might describe tidal forces with equations, but an interactive model shows them. A moon stretching like taffy as it nears its host planet, or a disguised world's orbit wobbling under gravitational stress. Digital planetariums take this further, projecting celestial misdirections onto dome screens where audiences can literally look up to see how early astronomers were fooled. Suddenly, the mystery object's path makes visceral sense. Its tilted, uneven orbit isn't a glitch but a fingerprint of capture, visible when you watch its trajectory spiral into place over eons compressed into seconds. These tools do more than teach, they democratize discovery. Amateur astronomers using free software like Stellarium have spotted anomalies in exoplanet transits that professional surveys missed. Classroom simulations have led students to ask questions about orbital resonances that even their instructors hadn't considered. When the Harvard-Smithsonian Center for Astrophysics released their worldwide telescope platform, they didn't just provide a cosmic map. They handed users the keys to reanalyze archival data, turning passive learners into active investigators. It's no coincidence that many of today's planetary scientists trace their passion back to childhood encounters with such tools. The bridge between experts and the public isn't built on simplified analogies, but on shared tools that preserve complexity while removing barriers. Consider how the Rubin Observatory's upcoming data releases will pair raw findings with citizen science platforms, inviting everyone to hunt for gravitational oddities in the same datasets professionals use. Or how the European Space Agency's Gaia Sky lets users fly through the Milky Way, toggling between modern measurements and historical star charts to see how perception has evolved. This isn't just education, it's empowerment, equipping the next generation to challenge assumptions and maybe, just maybe, catch the universe in another act of celestial disguise. What's truly revolutionary is how these models reframe failure. A student tweaking variables to force a stable orbit learns more from their mistakes, the chaotic ejections and collisions, than any perfect simulation could teach. In grappling with why certain parameters create a convincing moon illusion while others don't, They internalize the delicate balance of mass, velocity, and timing that governs real cosmic captures. The lesson transcends astronomy. It's a masterclass in uncertainty, a reminder that even the laws of physics leave room for surprises. And that might be the greatest gift these tools offer, not just understanding the cosmos as it is, but glimpsing how much wilder it could be. Naming a celestial body isn't just a scientific formality, it's a cultural act, a stamp of human imagination on the vast, impersonal cosmos. When astronomers first spotted our mislabeled planet moon, they likely assigned it a name from mythology or a numerical designation, never suspecting its true nature. But what if they'd known? Would it bear the name of a trickster god, a nod to its gravitational deception, or would it carry the moniker of a scientist who uncovered the truth? The process of naming space objects is surprisingly democratic yet fraught with tension, a blend of tradition, politics, and occasional outright rebellion. The International Astronomical Union, or IAU, oversees celestial nomenclature, aiming for consistency across languages and cultures. Moons often draw from mythological figures tied to their host planet's namesake. Jupiter's satellites honor Zeus's lovers and offspring, while Saturn's moons reference titans and giants. But when a new object defies categories, like our rogue planet moon, the rules blur. Imagine if it had been discovered today. Would the IAU classify it as a moon, triggering one naming convention, or as a dwarf planet, invoking another? The distinction might seem trivial, but names carry weight. Pluto's demotion didn't just change textbooks. It sparked emotional outcry because we'd anthropomorphized it as the plucky underdog of the solar system. Controversies erupt when naming feels exclusionary. In 2018, the public voted to name a distant Kuiper belt object Vulcan, a nod to Star Trek, only for the IAU to reject it for not fitting classical guidelines. Similarly, the asteroid formerly known as Bennu almost ended up with a corporate-sponsored name until backlash forced a course correction. These clashes reveal a deeper question: who owns the right to name the cosmos? Scientists, the public, the cultures whose myths are mined for inspiration. When indigenous astronomers pointed out that many IAU-approved names come from Eurocentric myths, the Union began collaborating with indigenous groups to incorporate more diverse traditions, a small but meaningful step toward equity. Consider the cultural ripple effects if our disguised planet had been correctly named centuries ago. In a world where comets were once seen as harbingers of doom, a planet caught masquerading as a moon might have inspired entirely new mythologies. The Maya, who tracked Venus with precision, could have woven its deception into their celestial warfare narratives. Medieval Europeans might have interpreted its orbit as a divine allegory of hidden truths. Instead, its misclassification rendered it a footnote, stripped of narrative potential until modern science corrected the record. The ethics of naming extend beyond fairness. They shape how we conceptualize space. Calling a world Eris after the Greek goddess of discord primes us to see it as chaotic, while Sedna, named for an Inuit sea spirit, evokes isolation and resilience. Had our planet moon hybrid been dubbed Loki instead of a dry catalog number, might it have captured public imagination sooner, spurring earlier investigations? Names aren't just labels, they're invitations to wonder, tools that can either gatekeep or democratize our relationship with the universe. This isn't just about the past. As we uncover more exoplanets and rogue worlds, the naming debates will intensify. Will we default to clinical alphanumeric codes or seize the chance to reflect humanity's collective stories? The choice matters because every name is a story, and in the end, the cosmos belongs to everyone who dares to look up. Our solar system, with its neat lineup of planets and orderly moons, might feel like the cosmic standard until you peek at the galaxy's wild diversity. Out there, worlds defy expectations at every turn. Planets that orbit their stars backward, moons larger than Mercury, and binary systems where two stars share a single planetary entourage. Among this chaos, our case of a planet mistaken for a moon starts to look less like an oddity and more like a hint of a hidden universal trend. Take Kepler 1625b, a gas giant with a suspected moon so massive it could qualify as a planet itself. Or the TRAPPIST-1 system, where 7 Earth-sized worlds dance so close together their gravitational tugs constantly reshape each other's orbits. If a moon-sized object can blur into planetary status there, why not in our own backyard? The real eye-opener comes from hot Jupiters, gas giants that hug their stars so tightly they complete orbits in days, not years. Many of these worlds shouldn't exist under old formation theories, yet they're astonishingly common. Their existence suggests planets migrate inward after birth, a gravitational shuffle that could easily fling smaller worlds into strange new roles. Imagine a Neptune-like planet drifting too close to its star, only to have its icy outer layers stripped away, leaving a rocky core that future astronomers might misclassify as a super-Earth. If planets can transform so radically, it's no stretch to think one might slip into a moon's orbit unnoticed. Then there are the rogue planets untethered from any star, wandering the galaxy's dark highways. Recent microlensing surveys suggest these nomads might outnumber stars in the Milky Way. Some could even host moons warmed by tidal forces or radioactive decay, mini solar systems without a sun. If a drifting planet were captured by a star or another planet, its moon-like appearance might endure for eons before someone spotted the truth. Our solar system's mix-up suddenly seems less like a fluke and more like a single note in a symphony of cosmic identity swaps. Pulsar planets add another twist. These worlds orbit the corpses of dead stars, survivors of supernova explosions that should have vaporized them. Their very existence proves planets can endure unthinkable violence and emerge unrecognizable. What's to stop a planet in such a system from being reshaped, relocated, or disguised by the chaos? Even in our comparatively quiet solar system, the late heavy bombardment, a period of intense asteroid strikes around 4 billion years ago, could have scattered and recaptured worlds like billiard balls. The more we study other systems, the clearer it becomes. Stability is the exception, not the rule. The ultimate test of our planet-moon hypothesis lies in the Kepler data trove. Among its thousands of exoplanet candidates, astronomers have spotted Tatooine worlds orbiting binary stars, planets with rings 200 times wider than Saturn's, and even cotton candy, planets with densities lower than styrofoam. Yet exomoons remain elusive, their faint signals drowned in stellar glare. When we do find them, like the possible gas giant moon Kepler 1625b, their orbits often look nothing like our solar system's tidy satellites. Some loop wildly, others hover improbably close to their host planets, as if barely clinging to gravitational sanity. These aren't just moons, they're survivors of cosmic upheaval, their paths etched by forces we're only beginning to map. This galactic census reveals a humbling truth. Our solar system isn't the template for how planets behave. It's just one permutation in an infinite cosmic experiment. The same gravitational forces that disguised a planet as a moon here might be weaving stranger deceptions elsewhere. Maybe in a distant system, a gas giant's moon hides an Earth-like atmosphere under icy crusts, or a binary planet pair passes for a star and its companion. The universe thrives on blurred lines and borrowed identities, reminding us that every time we think we've cracked the celestial code, the cosmos hands us a new riddle wrapped in starlight. Beneath the icy crusts of moons like Europa and Enceladus, vast oceans slosh in perpetual darkness, warmed by the gravitational squeeze of their host planets. These hidden seas, shielded from the cold vacuum of space, have become prime targets in the hunt for extraterrestrial life. But what if we've been overlooking an even more tantalizing possibility? Imagine a world with the size and geology of a planet, rocky, geologically active, perhaps even boasting a thin atmosphere, disguised as just another moon. If gravity can trick us into mislabeling an entire planet, could it also be hiding a habitable world in plain sight? The concept of habitability stretches far beyond the traditional Goldilocks zone, that narrow band around a star where liquid water can exist. Tidal heating, the same force that churns Europa's subsurface ocean, could transform a captured planet moon into an unlikely oasis. Picture a Mars-sized body, snagged by a gas giant's gravity and locked in an eccentric orbit. Each close pass would flex its interior, generating heat through friction. Over time, that energy might melt ice into sprawling subsurface lakes or power hydrothermal vents akin to those on Earth's ocean floors, where life thrives without sunlight. The ingredients are all there: liquid water, organic molecules from comet impacts, and a steady energy source. All that's missing is our ability to recognize such worlds for what they truly are. This revelation flips the script on how we define habitable environments. Moons were long considered afterthoughts in the search for life, small, frozen, and dependent on their host planets for warmth. But a planet masquerading as a moon could rewrite those assumptions. Its larger mass might retain heat more effectively, or its metallic core could generate a protective magnetic field, something most moons lack. Even its atmosphere, if it survived capture, could be replenished by volcanic outgassing. Suddenly, the list of potential life-bearing worlds expands beyond Earth like exoplanets to include these gravitational imposters, hiding in the shadows of their larger siblings. The implications for astrobiology are staggering. Consider Jupiter's moon Callisto. Though icy and seemingly inert, it shows hints of a subsurface ocean. Now imagine a captured planet with twice Callisto's size and 10 times its internal heat. What mysteries might lurk beneath its surface? Or take Titan, Saturn's methane-rich moon, where rivers of hydrocarbons carve valleys into frozen landscapes. A Titan-like world with the mass of Mercury could have even thicker atmospheres and more complex chemistry, blurring the line between moon and planet in ways that matter profoundly for life. This isn't just speculation, it's a call to rethink our tools. Traditional methods for detecting habitable exoplanets focus on starlight filtering through atmospheres or the subtle dimming caused by transiting worlds. But a moon-sized planet orbiting a gas giant would require new approaches. Maybe it's the gravitational wobble it imposes on its host, or the infrared glow of tidal heating betraying its presence. The upcoming James Webb Space Telescope, with its unparalleled sensitivity to heat signatures, might be the key to spotting these cosmic double agents. Ultimately, the search for life demands humility. The universe has a habit of surprising us, whether it's extremophiles thriving in Earth's deepest mines or the possibility of planets hiding as moons. Every time we think we've nailed down the rules for habitability, nature throws a curveball, a world where sunlight never reaches, yet life might flourish, or a rogue planet adrift between stars, warmed only by radioactive decay. If there's one lesson from our solar system's disguised planet moon, it's that the boundaries we draw are often illusions. Life, if it exists out there, won't care about our labels. It will thrive where it can, in whatever niches gravity and chemistry allow, even in places we haven't thought to look yet. gravity's rulebook gets tossed out the window when we venture beyond our solar system into the strangest corners of the cosmos. Near black holes, space-time warps so violently that light itself bends into inescapable loops, creating gravitational funhouse mirrors where up and down lose all meaning. Stars orbiting the Milky Way's core move too fast for the visible matter holding them, hinting at dark matter's invisible scaffolding weaving through galaxies. Then there's Planet Nine's hypothetical tug on Kuiper belt objects, a gravitational ghost that may or may not exist. These aren't just quirks, they're screaming reminders that for all Newton and Einstein revealed, gravity's full story remains half-written. Take the case of fast radio bursts, a cosmic radio signal so powerful they outshine entire galaxies for milliseconds. Some theories suggest these could be neutron stars colliding, or even alien propulsion, though that's wildly speculative. But the real stumper, their trajectories hint at passing through gravitational lenses we can't locate, as if invisible mass is bending their paths. It's like hearing an echo in a room where no walls exist. Similarly, the Hubble tension pits two methods of measuring the universe's expansion against each other, with results differing by just enough to suggest an unseen force. Perhaps a new flavor of gravity is at play. Even more baffling are the galaxies that rotate as if they're solid disks defying Kepler's laws. According to orbital mechanics, their outer stars should lag behind like runners losing steam, yet they keep pace with inner stars as though glued to an invisible turntable. Dark matter is the usual suspect, but alternative theories propose gravity itself behaves differently at galactic scales, a tweak to Einstein's relativity that could upend cosmology. The Bullet cluster, where two galaxy clusters collided, offers eerie evidence. X-ray maps show most visible matter stuck in the middle, while gravitational lensing reveals mass far ahead, as if something invisible sprinted through the wreckage. These anomalies aren't just academic riddles, they're breadcrumbs leading to deeper truths. When LIGO detected gravitational waves from colliding black holes in 2015, it didn't just confirm Einstein. It revealed black holes merging faster than models predicted, suggesting their dance is governed by physics we've yet to grasp. And let's not forget quasi-satellites like Earth's companion Kamoa, an asteroid that orbits the Sun in sync with us, mimicking a moon through gravitational sleight of hand. What ties these puzzles to our planet moon mix-up is their shared lesson. Gravity is the universe's greatest illusionist. Just as it disguised a planet as a moon in our backyard, it's orchestrating grander deceptions across the cosmos. Each anomaly is a clue, a challenge to look past what we expect and embrace the beautiful chaos of what's really out there. The day we stop being surprised by gravity's tricks is the day we stop truly exploring. Amateur astronomers have long been the unsung heroes of cosmic discovery, proving time and again that you don't need a PhD or a multi-million-dollar telescope to rewrite the textbooks. Take the case of Japanese hobbyist astronomer Yuji Hyakutake, who in 1996 spotted the brilliant comet bearing his name using nothing but a pair of binoculars. Or British amateur George Alcock, who discovered 5 nova and 2 comets from his backyard, memorizing thousands of star patterns to spot the faintest anomalies. These aren't just lucky breaks, they're testaments to the power of patient, passionate observation. Now imagine applying that same dedication to hunting for disguised planets lurking in our solar system. With today's affordable high-resolution cameras and tracking mounts, backyard stargazers can capture planetary motions with precision that would have dazzled professional astronomers a century ago. The rise of citizen science platforms has turned this potential into a revolution. Projects like Zooniverse's Planet Hunters or NASA Backyard Worlds invite anyone with an internet connection to sift through telescope data, flagging oddities that algorithms might miss. In 2017, a German schoolteacher scanning images on Disk Detective org helped identify a gas giant exoplanet orbiting a young star, proof that cosmic breakthroughs aren't confined to elite institutions. For our hypothetical planet moon imposter, the key might lie in subtle orbital quirks, a moon that wobbles unpredictably, or a satellite whose reflected light spectrum doesn't match its supposed composition. Amateurs equipped with spectroscopy attachments could potentially spot these red flags, especially when monitoring the outer solar system's faint, slow-moving objects over months or years. What makes amateur contributions so invaluable is their sheer volume. While professional observatories must ration telescope time for high-priority targets, backyard astronomers can monitor the same patch of sky night after night, building datasets that reveal gradual changes. The American Association of Variable Star Observers, a network of amateurs founded in 1911, has logged millions of brightness measurements that professionals use to study stellar evolution. Similarly, the All-Sky Automated Survey for Supernova relies on volunteers to scan for sudden stellar explosions. This distributed model is perfect for catching gravitational oddballs objects whose orbits or behaviors deviate just enough to hint at hidden identities. Technology is leveling the playing field further. Affordable robotic telescopes like those offered by SLU or the Los Cumbres Observatory let amateurs control instruments remotely, capturing data that rivals professional quality. Open-source software such as AstroImage.J enables precise photometry, measuring celestial brightness variations that might betray a moon's planetary origins. Even smartphone apps like Sky Safari now integrate databases of known objects, making it easier to spot interlopers hiding among catalogued moons. The next great discovery might come from a retiree in Arizona tracking Jupiter's irregular satellites, or a teenager in Norway analyzing light curves from their balcony. This democratization of discovery does more than advance science. It reshapes who gets to participate in humanity's cosmic conversation. When the International Astronomical Union names a newfound object, it often honors both the professional who confirmed it and the amateur who first raised the alarm. That inclusivity matters because the universe doesn't discriminate between Ivy League labs and suburban rooftops when it hides its secrets. Every time a hobbyist's observation corrects an astronomical assumption, whether spotting a supernova or challenging a moon's classification, it reaffirms that curiosity, not credentials, is the real engine of exploration. So keep looking up. That faint dot near Saturn tonight, it might be just another icy moon, or it could be a planetary fugitive hiding in plain sight until someone with sharp eyes and a stubborn streak decides to dig deeper. After all, gravity's greatest illusions are no match for collective human curiosity. Labels like planet or moon feel set in stone, etched into textbooks as if the universe itself handed them down. But peel back the layers, and you'll find these categories are more like temporary placeholders, human attempts to corral cosmic chaos into tidy boxes. Think about it. We draw lines between stars and planets based on nuclear fusion, between planets and moons based on orbits, but nature doesn't play by these rules. It's as if we're trying to divide a rainbow into discrete color blocks when the reality is a seamless spectrum. Our mystery object, the planet disguised as a moon, exposes this tension perfectly. It's not just an astronomical oddity, it's a mirror held up to how we impose meaning on the cosmos. Consider how much weight we place on origins. A moon formed from the same primordial disk as its planet is deemed true, while a captured world is labeled an imposter. But does gravity care about pedigree? A planet snagged by another's pull and forced into orbit doesn't suddenly stop being what it is. It's still a world with geology, chemistry, and potential. The distinction says more about our need for clean narratives than about the objects themselves. Ancient philosophers like Aristotle saw the heavens as immutable and perfect, a realm apart from Earth's messiness. Today, we know better, yet we still cling to taxonomies that assume celestial bodies fit neatly into slots. This isn't just academic noodling. Definitions shape exploration. If we rigidly classify Europa as just a moon, we might overlook its subsurface ocean's potential for life. If we dismiss Pluto as a dwarf planet, we risk underestimating the complexity of Kuiper belt objects. The moment we mistake a planet for a moon, we're not just misplacing a label, we're potentially overlooking an entire world story. The philosopher Thomas Kuhn argued that scientific progress often hinges on paradigm shifts, moments when old frameworks crack under the weight of new evidence. Our cosmic masquerade could be one such crack, urging us to rethink how we categorize what we find. At the heart of this is a deeper question: why do we classify at all? Partly for practicality, it's easier to study objects when they're grouped by shared traits, but there's also an innate human drive to make the unfamiliar familiar, to tame the vast unknown with language. The irony is that the universe resists this, from quantum particles that defy position to black holes that warp causality. Nature thrives on ambiguity. Our mystery object embodies this defiance, sitting at the crossroads of multiple definitions, refusing to conform. Perhaps the most humbling realization is that our labels are time-bound. A century ago, planet meant whatever we could see orbiting the sun with crude telescopes. Today, it's a contested term tangled in orbital dynamics and neighborhood-clearing debates. A century from now, it might mean something we can't yet imagine. The cosmos doesn't change, our understanding does. Every time we catch gravity in a lie, like a planet pretending to be a moon, we're reminded that the universe isn't just stranger than we suppose, but stranger than we can suppose. And that's where science and philosophy meet, in the awe of realizing that every answer unveils new questions, and every category we create is, at best, a work in progress. Every leap forward in astronomy begins with the same humbling truth: we can only see as far as our tools allow. Picture Galileo squinting through his rudimentary telescope in 1609, sketching the jagged shadows on the moon's surface, a revelation that shattered the ancient belief in perfect celestial spheres. Fast forward to the mid-19th century, when the first photographic plates captured stars as more than fleeting points of light, preserving their positions for precise measurement. Each of these breakthroughs didn't just add to our knowledge, they rewrote the rules of what was possible. The mystery of our disguised planet-moon hybrid couldn't have been unraveled with Galileo's brass tube or even the finest glass lenses of the 1800s. It took 20th century innovations like charge-coupled devices, or CCD, the same technology in your smartphone camera, to detect the subtle gravitational wobbles betraying its true nature. Consider how much we missed before these tools existed. Early star catalogs logged positions but couldn't measure mass. Telescopes tracked motion but couldn't analyze composition. The planet-moon mix-up persisted for centuries, not because astronomers were careless, but because they lacked the means to see beyond the illusion. Spectroscopy, the art of splitting light into rainbows to read cosmic fingerprints, was the first crack in the facade. When applied to our mystery object, it revealed atmospheric gases and surface minerals alien to nearby moons. Then came radar astronomy, bouncing radio waves off celestial bodies to map their shapes and rotations, exposing an oddly bulging equator that didn't match a typical satellite's profile. These weren't just incremental upgrades, They were entirely new senses for perceiving the universe. The real turning point arrived with space-based observatories, free from Earth's distorting atmosphere. The Hubble Space Telescope's crisp vision resolved surface details suggesting tectonic activity, while the Chandra X-ray Observatory spotted unexpected heat radiating from what should have been a frozen relic. Down on Earth, interferometry linking multiple telescopes into a virtual instrument the size of a continent pinpointed the object's gravitational influence on its host planet with micrometer precision. Suddenly, the numbers didn't add up. This was no mere moon, but something with planetary mass wearing a celestial disguise. Yet for all these advances, the most revealing breakthroughs often come from repurposing old tools in new ways. Take adaptive optics, originally developed for spy satellites to sharpen images through atmospheric turbulence. When adapted to ground-based telescopes, it cancelled out the twinkle of starlight, revealing subtle orbital anomalies around our target object. Or consider gravitational wave detectors like LIGO, designed to catch ripples in spacetime from colliding black holes. By analyzing how the object's gravity warped passing starlight, a technique called microlensing, researchers could weigh it indirectly, confirming its planetary density. What's thrilling is how these technological threads weave together. The object's infrared signature, measured by the Spitzer Space Telescope, hinted at internal heat from tidal friction. Its radio emissions, picked up by the Very Large Array, suggested a metallic core. Each dataset alone was a puzzle piece. Combined, they formed an unmistakable portrait of a captured planet. This synergy between instruments underscores a vital lesson. No single tool holds all the answers. Just as a doctor uses X-rays, blood tests, and MRIs to diagnose a patient, astronomers need multiple wavelengths and methods to decode cosmic mysteries. The implications stretch far beyond one misclassified object. Every time we push technology's boundaries, we uncover phenomena that demand even better tools. The James Webb Space Telescope's infrared eyes might spot similar planet-moon hybrids around other stars, while NASA's upcoming Nancy Grace Roman Space Telescope could catch them in the act of being captured. On the horizon, 30-meter class ground telescopes will dissect exomoon atmospheres for biosignatures, and quantum sensors could measure gravitational fields with unprecedented sensitivity. Each innovation promises to expose new layers of cosmic deception, perhaps revealing that our solar system's mix-up is just the tip of the iceberg. This isn't merely about gadgetry, it's a testament to human curiosity. The engineers who crafted Hubble's corrective lenses, the coders who train AI to sift through petabytes of telescope data, the theorists who dream up entirely new ways to probe gravity, they're all part of a chain stretching back to the first stargazers. Their collective work reminds us that the universe's greatest secrets aren't hidden in darkness, but in the blind spots of our own ingenuity. And if history is any guide, today's cutting-edge tools are already planting the seeds for tomorrow's revolutions, the ones that'll make our current marvels look as quaint as Galileo's first telescope. Gravity's greatest trick wasn't hiding a planet in plain sight. It was revealing how much we still have to learn. This cosmic case of mistaken identity isn't just a quirky footnote in astronomy. It's a masterclass in humility. For centuries, we labeled, catalogued, and mapped the heavens, confident we'd sorted the universe into neat boxes. Then, like a magician revealing the hidden card, gravity showed us the flaw in our assumptions. That's the real magic here, not just the discovery itself, but what it says about the nature of science. Every time we think we've got the cosmos figured out, it throws us a curveball, whether it's a rogue planet playing dress-up or dark matter bending galaxies in ways we can't yet explain. What makes this story so compelling is how it mirrors the broader journey of scientific progress. Imagine the astronomers who first sketched this object's path. They weren't wrong so much as incomplete, working with the tools and knowledge of their time. Science doesn't move in straight lines, it zigzags, doubling back to correct old ideas while stumbling onto new ones. The shift from seeing this object as a moon to recognizing it as a captured planet wasn't a failure, it was evolution. Like upgrading from a blurry black and white photo to a high-definition 3D model, each generation of technology and theory brings us closer to the truth, even if that truth is messier than we'd like. And let's not forget the human element. Behind every cosmic revelation are people curious, stubborn, and occasionally wrong, but always pushing forward. The researcher who first noticed the orbital discrepancies, the grad student who ran the simulations that didn't quite fit, the amateur astronomer who spotted an anomaly in their backyard telescope data. Science is a collective effort, a slow churning machine that turns questions into answers, and sometimes answers back into better questions. That's why stories like this matter. They remind us that discovery isn't reserved for geniuses in ivory towers, but for anyone willing to look up and wonder. So what's next? If gravity could pull off this illusion in our own solar system, what other sleights of hand are waiting to be exposed? Maybe we'll find moons masquerading as asteroids or binary planets hiding in the Kuiper belt. Perhaps the James Webb Space Telescope will spot an exomoon with an atmosphere thick enough to breathe, or a future probe will uncover tidal heated oceans on a world we've barely noticed. The universe loves a good plot twist, and we've only just cracked the first chapter. Here's the real takeaway: the cosmos isn't a static backdrop, but a living, changing story where even the laws of physics have room for surprises. Our job isn't to fit everything into tidy categories, but to stay open to the chaos, the exceptions, and the glorious unpredictability of it all. So keep questioning, keep exploring, and most of all, keep looking up, because the next great cosmic revelation might be hiding in the last place you'd think to check. And who knows, the next time gravity plays a trick on us, you might be the one to catch it. Before you go, drop a comment below. What's the wildest cosmic mix-up you can imagine? A star pretending to be a planet, a black hole disguised as a moon. The universe is stranger than fiction, and your ideas might just spark the next big discovery. Don't forget to like and subscribe for more journeys to the edge of what we know and what we don't. The cosmos is full of secrets, and together we're just getting started.